Recording is rolling. It is Wednesday, January 11th, and we're going to do this spring oscillation lab. Now, this is here. Uh, last couple of days, we've been looking at this pendulum lab, but mostly Monday. We just finished it up yesterday, these graphs. Right? So you guys have the pendulum lab finished. Right? But the opposite side of the same paper, I printed this other lab. Right? So we're going to figure out today what is the spring constant some particular spring, right? I have a bunch of springs back there, kind of like this. There's different ones, different stiffnesses, but just pick one particular spring. There's like a whole box of lab weights. Like I have a couple lab weights up here, but you can use the different lab weights to figure this out. Like how stiff is the spring? Now, there's actually two formulas that you guys have seen at this point in this class for that involve spring constant, like how stiff is the spring. Like, and one goes back a long way back in this class a few months ago. You guys remember Hooke's law? Hooke's law, right? The relationship between how much force you put on to stretch it and how much it actually stretches. In this case, the force can be provided by a weight. Right? Well, and the other equal opposite force, the robot force, can be provided by your hand. You can hold it. Or I drew it with a spring scale here, but you don't actually have to use a spring scale for this lab. Right. So let me divvy this paper in half because there's like two halves to this lab. Right. The this left half, which involves Hooke's law, and this right half, which is going to involve oscillation, which is well, one thing at a time here. So going back a few months in this class, Hooke's law. Okay. You guys remember the formula for Hooke's law? F equals kx. You guys remember F equals kx? Okay. So you remember that from first semester. So F is the force you put on it, which in this case is provided by the weight. Ooh, there's some mass here, mass times gravity field, that could be weight, could act as the force. Okay. And then what does K represent in this equation? Spring constant. How stiff is the spring? And what does X represent? How much it stretched from its equilibrium point? Okay. Or in some cases compressed, but not with these particular springs. You can't really compress the springs, but you can stretch it. So if this was like unstretched, and then if you put either a ruler or a meter stick next to it, okay, let this hang down. Oops, kind of around. I could say side view. Suppose this is like vertical, right? Suppose it hangs down like 5 centimeters. It's like at 5 centimeters, right? Is it the stretch that could be your X, right? Now, there's actually a couple different X's you're interested in today. That would be like X equilibrium, right? Wouldn't just be equilibrium, just hanging out there. Okay. Hey, what if you did this instead? Okay. No, this is more related to the next part of the slide, but suppose you start from here. Again, side point of view, supposed to like down is this way, gravity's pulling this way. Okay. And you just drop it, and it shoots past that equilibrium position and stretches to maximal, and then eventually reaches an equilibrium. Okay. Ooh, X max would be different from X equilibrium, wouldn't it? Which X does this refer to? Is this X max or X equilibrium? Oh, and here's the picture this goes with. Okay. So hook on the lab weight here, drop it. It overshoots, stretches some maximal amount, and then eventually, after some oscillation, maybe it eventually comes to rest like right here. That's X equilibrium. Okay. Hooke's law, which X is this? Equilibrium. Yeah, that's X equilibrium. So I mean, this K times X equilibrium. Right. It's equilibrium. Right? Right, now, sort of the goal you're looking for today is what is the spring constant? Right? And this is the old method. You guys have known how to do this for a few months now, right? I think we did some of this last semester, lab one. So can you guys do one algebra step to solve for the spring constant K? Would that just be K is equal to the weight, divided by X equilibrium? Just like that. Right. That's one way you could get the spring constant, right? How stiff is the spring? You could do that, right? Okay. You guys got that? Right. That's sort of the main idea of the first step. Let's look at this table, see how the ideas go down here. Because I want to do a couple of little modifications. Okay. Right, so to get through this, you've got your spring, you hook on the weight, let it drop as it just starts oscillating, right? And then eventually comes to rest. Can you grab the maximum stretch value? Can you grab the equilibrium value? Right? And if you use conservation of energy versus equilibrium, you could show that theoretically this should be a 2-to-1 ratio. Now, empirically, it is whatever it is. It might not be exactly that, but well, you guys are going to find out. You guys are going to graph it and see how close that is. Okay? Right, so let's look at this table. mass in kilograms. So for example, if you had this guy says 100 grams. It says 100 grams right there. Guys, 100 grams. How many kilograms does that equal to? 0.1. Okay. So, would that be the mass in kilograms? 0.1. So if I had this guy exactly, I would put 0.1 kilograms right here. Right. All right. Then these two columns, X max and X equilibrium. Well, you guys see that what that is from the picture, right? I just went over that X max to X equilibrium. Okay. You guys see that? Oh, this column, this fourth column says the force reading of the scale at equilibrium. I want to modify that a little bit. Scratch that out, and instead of force on the scale, don't worry about spring scales. Okay, just put mg above it, mg. Okay. And through another column over here, it says g, because you guys know what gravity field we're in. We're in either 9.8 or 10 meters per second squared. Just pick your favorite value, right? Okay. So back to picking out numbers. We're back to this guy. Right? You guys told me 100 grams is 0.1 kilograms. Is 0.1 kilograms weighs how many newtons? What's 0.1 kilograms times, there you go. 0.1 kilograms times 10 meters per second squared is 1 Newton. This guy has a gravity force downward of 1 Newton, right? So any lab weight smaller than this is going to be less than 1 Newton. Anything bigger than this is going to be more than 1 Newton. Okay? And if you use 100 grams, that's 1 Newton goes right there. Boom, that's up. Now you're going to switch out different lab masses. So each row is going to be unique, different lab masses, but using the same spring over and over, the same spring, okay? Different lab weights. Okay. And finally, last column, K. Well, I just showed you guys how to do that. Okay. You're going to take the weight in newtons and divide by the stretch amount at the equilibrium point, right? And I'll tell you what the spring stiffness is. Right? Yeah, that's like an old method. That's like a first semester type method. Okay. Okay. And it spells out exactly how to do it right there. You guys see that? And there's a couple of graphs. This one is like the Hooke's law graph. So weight versus the stretch amount at equilibrium. Okay. What do you guys think this graph's gonna look like? It's gonna be a direct relationship, probably, like Hooke's law, F equals kx kind of deal, right? That's kind of what that is, right? Can you guys scale the axes? Because I have them labeled already. Can you guys scale those and plot coordinates? Right? Like you're just pulling Cartesian coordinates from this table, right? And the graph on top that's where I wanted you to see what is this compared to this, right? I think this should be a 2-to-1 ratio. Theoretically, it should be. You guys see that's the case. Here, let me do a little side quest here. I want to show you guys why I'm saying 2-to-1. Right. So we got this already for equilibrium. Right. How much is stretch? Can I rearrange that a little bit? You got x equilibrium is cross multiply that, divide the k down, mg divided by k. Is that okay? Okay. So x equilibrium. Zoom out here a little bit. Just do a little side thought right here. X equilibrium would be the weight hanging on it divided by the spring constant. Okay. Right. Now that's equilibrium. That comes from Hooke's law. That's just rearranged. Okay. But how would you like calculate just on paper what the maximum stretch amount should be? Okay. Now this is also a first semester concept. Because if you see a height change and a spring changing length, that's going to be what framework to solve this? Conservation of energy. Okay, so let's try that out. Sum of energy initial equals sum of energy final. Okay, what type of energy? All the top here before the string stretched. Up here. Is it gravitational potential? Right? And then, okay, loose gravitational potential is falling. And at this point, there's no kinetic here or here because it's not moving here or here. So where'd all the energy go? Into the spring. Yeah, the spring potential. So at the top, it's all mgh, but instead of h, I'm going to call it x max because I care about this whole thing, right? Call this height 0 down here. Okay. And at the bottom, it's all 1/2 kx squared. And that x is also x max again. So one of these x maxes cancels. Let's solve for the other one. Times 2 divided by k. X max is 2 times this mg divided by this k. Oh, look at that. Compare this side by side. X equilibrium compared to x max. You guys see x max should be 2 times x equilibrium. You guys see that? Right. That's on paper anyway, but you guys are going to get actual empirical data and see how true is that actually. Okay. So that's just a little side thought there. All right, you guys good so far? All right, now let's move on to the oscillation half of the slab, so the right half. Okay. Now, what you're going to do here is you just use the same spring over and over. Just one spring. You can use this entire lab. Again, you guys, a whole box of lab weights. I just got one up here, right? You gotta hook it here. Right? So you change out the mass for each row, right? Okay. And you're gonna pull up and let it go, and it's gonna oscillate. Here, so that just like oscillating up and down. Okay. So I would count like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Do you guys bring your stopwatches today? You guys got stopwatches? Can you guys count? Okay, so mass in kilograms. So this is 0.1 kilograms. Time for oscillation, however many seconds. Let's say it's like 7 seconds. What would the time for one oscillation be? 0.7 seconds? Just this divided by 10. Right? All right, now here's the oscillation way to get spring constant. Because this is the other formula that you guys see spring constant. The first one was 12, but we just went through all that. Here's the other place you guys see spring constant. This is the new one, right? Right. So can you solve for K? Let's do some algebra here. If you take this time period, divide by the 2 pi, square both sides to unvary it from the square root, maybe divide this mass over and take the circle of the whole thing, right? A few algebra steps. You do some algebra, right? Okay. And that is this right here. Oh, look at that, K. You got 2 pi quantity squared times mass divided by t time period squared. Boom. Okay. Now there's one more thing that I wanted to show you guys, and that's related to this graph, because I want you to make one more graph. And you guys are gonna scale the graph. You guys can plot some points. I did already throw the axes on here for you. I put mass in kilograms on the vertical, and time period squared divided by 2 pi quantity squared on the horizontal. What the heck is that about? Right? That has to do with sort of this right here. It's a way to linearize it so that the slope is equal to K. So it's linearized, but not exactly the way on this poster, but a little bit different way. Let me show you guys. So if you start from this, I'll show you guys where this comes from. So here's the oscillation half of the lab. Right, we're on. So did Hooke's law already. Now we're on to oscillation. Okay. I know time period is equal to 2 pi times the square root of m over k. Or we're going to say we know that. Right? Did a very similar lab a couple of days ago. A couple of days ago with the pendulum, we were like assuming we were cavemen and we were trying to figure this out from scratch. Today we're going to say, suppose you pull this from a textbook. It's like, okay, well, let's see how true this is. Okay. Okay. So remember, our goal is to get k, but from this perspective now, this oscillating perspective. So I need to unbury this from the square root. Ooh, maybe I should square both sides. Okay, so now it's unburied from the square root. But it's in the denominator. Okay. Ooh, maybe I should cross multiply it up. And while I do that, I'm going to swap both sides while I'm at it. So I'm going to get 2 pi quantity squared m is equal to k times time period squared. Right? Actually, that could solve it by itself. If you want to make it look exactly like the axis I set up, you take this 2 pi quantity squared and divide it down. You get mass is equal to spring constant times time period squared divided by 2 pi quantity squared, like that. Like I said. Okay. Do you guys see how this looks like the form y equals mx in terms of algebra? Right, where y, m, and x are like y-axis, slope, and x-axis. Y equals slope times x. You guys see that? Okay. So here's your y-axis, m, mass in kilograms. Oh, look at that, mass in kilograms. Here's your x-axis, time period squared divided by 2 pi quantity squared. Oh, look at that. That's your x-axis. And the unit is square seconds. Right, you guys see that too? Okay. So do you guys think that this is probably going to line up all these points in a straight line? Plot it and see if that's true. I bet it's probably pretty close to true. Right? And then it's set up in such a way that the slope is exactly equal to the spring constant. Okay. So there you go. You got 2 different perspectives for how to get spring constant. Right? You guys got Hooke's law from last semester, and you guys got this oscillation method. Okay. Okay. So I'll walk around, help you guys back in the lab area. Again, all you need is one spring and a box of lab weights, so you can change out the mass, right, per trial. Made a couple little modifications here. Yeah, once you got all your data, you can graph these 2 graphs, make sure you scale, label them, plot the points, line best fit, and then turn that into the grade tray. You should have just enough time. So everything is back there. If you don't do all 5 rows, that's okay. If you get at least 3 or 4 points, get at least 3 or 4 of these, at least 3 or 4 of these, you'll have enough data. Right? So I'll walk around, help you guys out. Once you got all the graphs, turn it into the grade tray. Grade tray.